So these are the 7 fundamental or base quantities. Now, what about their units? Because you recall, we said earlier that a physical quantity has a magnitude, and in most cases, it has a unit as well. Now, the units for these fundamental or base quantities are also referred to as fundamental or base units, right? Let's talk about them. The SI unit for length is the meter, and the symbol for meter is M, right? So we have the base quantity, and we'll put their respective base units. So the first one, of course, is length, and we'll put the symbol in brackets. The SI unit of length is the meter, and the symbol for meter is a lowercase m. Next is mass, and the symbol for mass is a lowercase m as well. The SI unit for mass is the kilogram. So this is a kilogram, kg. The next is time, symbol T, units, SI units, the second, symbol S. Length, mass, time, temperature, theta. Now, many students have become accustomed to using a particular unit for temperature, degrees Celsius, right? Now, whereas the degree Celsius is an acceptable unit for temperature, especially when dealing with heat-related topics, the SI unit of temperature is not the degree Celsius, but the Kelvin. So the SI unit for temperature is the Kelvin, symbol K. Next one is electric current, symbol I, and the SI unit of electric current is the ampere. Symbol for an ampere is uppercase A. So we have 1, 2, 3, 4, 5. What's missing? Amount of substance. Amount of substance. And for that, we'll use the symbol N. And the SI unit for the amount of substance is the mole. And of course, if you're doing chemistry, or if you did chemistry, you would have encountered this one quite frequently. The symbol for mole is almost the entire word, but with the E drop off, mole, MOL. And lastly, luminous intensity. The symbol for which is an I with a subscript V, and the SI unit for luminous intensity is the candela. Symbol for which is CD. So the SI unit for luminous intensity is the candela. So these are the 7 fundamental or base quantities and their respective base units. Now earlier we said that basically these are the foundation or the building blocks of all other physical quantities. So there's no physical quantity which cannot be expressed as a combination of one or more of these, right? And the respective units, of course, are called base units or fundamental units. So symbol for length is L, SI unit is a meter, symbol M. The symbol for mass is also M. Now, the question may arise is, one question which may arise is, if you see the symbol M, how do you tell if it's used to represent a meter as opposed to mass? Now, let's differentiate between physical quantities and their units. So suppose I write down L equals 20 meters. Now, at a certain stage, you will become familiar with the symbols for the particular physical quantities, and therefore you don't have to spell out the word. So if you're asked to write down a length, you don't have to spell out the word length. You can actually use a symbol L, and anybody who has a certain knowledge of, say, physics will understand what L means, especially, of course, if you include the unit as well as the magnitude. So if you write down L equals 20 m, then somebody will be able to look at this and interpret as a length of 20 meters. So the length, being the physical quantity, of course, comes on the left-hand side of the equal sign. You begin the statement by writing the physical quantity, and of course on the right-hand side we have the magnitude as well as the unit, right? If you write down this, m equals 50 kgs, then that, of course, you should be able to interpret as stating the mass of a physical quantity. Could be any large object. So m equals 50 kg, so 50 kilograms. So what we see is that basically the physical quantity always comes on the left-hand side of the equation, and the magnitude and unit, they always come on the right. So once you understand that, then there's the possibility of actually confusing the meter, m for meter, with m for mass significantly decreases, right? So those are our base quantities and their respective units. Now let's look at the other type of physical quantities, rather, what we call derived quantities. So derived quantities. Now, what exactly is a derived quantity? Derived quantities, as the name suggests, are quantities which have been derived from the base quantities, right? Now, usually, of course, whenever we're trying to define a term, we try not to use back the word in the definition. But in this case, basically, we could just use a synonym for derived, but essentially that is what is taking place. Derived quantities are quantities which have been derived, or we may say formulated, from fundamental or base quantities. So look at the 7 fundamental or base quantities, and any physical quantity which does not belong to that list is therefore a derived quantity. So what are some examples of derived quantities? We can speak about density. We can speak about volume. We can speak about pressure. We can talk about speed. We can talk about velocity. So these are all examples of derived quantities, right? And these can be expressed in terms of their fundamental or base quantities, right? So examples of derived quantities: density, volume, pressure, speed, velocity. And of course, this list is by no means exhaustive. As you go deeper into the subject, we will be introduced to many more derived quantities, right? Of course, the list of fundamental quantities is complete, and therefore none will be added to it. However, the list of derived quantities that we'll be exposed to will keep on increasing, right? So these are a few examples of derived quantities. Now, quantities which have been derived from fundamental or base quantities are called derived quantities. Now, what about their units? Their units are also called derived units, right? Now, derived quantities usually have a definition. For instance, what is density? Density is the mass per unit volume of a substance. So density is the mass per unit volume of a substance. So if you're asked to define density, you would basically write something to the effect of: density is the mass per unit volume of a substance, right? Now that's the definition. Many of these derived quantities, or all of them, there will also exist what is called a defining equation, which will allow you to calculate this particular physical quantity. In many cases, the defining equation is directly related to the definition, not all cases. However, the defining equation should never be used as a substitute or a replacement for the definition. So if you're asked to give a definition for density, it's supposed to be a worded statement, not an equation. So what is it? Deriving the defining equation for density. So we can write that density equals mass divided by volume, right? So this is the defining equation for density. Regardless of the nature of the particular material, if we want to find its density and we have a certain mass and we have a certain volume of it, or if we can determine its mass and determine its volume, we can simply determine its density by dividing its mass by its volume. So as I mentioned before, in many cases, the defining equations are directly related to the definitions, but should never be used as a substitute or a replacement for the definition. Now, at the CSEC level, for instance, if you were asked to define density and you simply wrote down density equals mass over volume, the teacher may have been lenient and may have given you the marks, but in reality, at this level, defining equation is simply not acceptable for the definition of a physical quantity. When asked to define a physical quantity, you're expected to write a statement, a worded statement, right? What about pressure? What is the definition of pressure? Pressure is defined as the force acting normally per unit surface area. So pressure, the force acting normally per unit surface area. So that is the definition of pressure. And of course, the word normally in physics basically means at right angles to or perpendicular to. That is the definition of pressure. And pressure is another of those physical quantities where the defining equation and the definition are related, right? So to calculate pressure, we basically use the formula pressure is equal to the force divided by the area over which the force acts. And of course, this force will be known to be a perpendicular force. So if we're calculating the pressure exerted by a particular force on a certain area, then the force is the perpendicular force, right? If we talk about speed, speed is defined as the rate of change of distance with time, right? So speed is the rate of change of distance with time, and of course the formula for calculating speed is also related to the definition. Velocity or speed, of course, are similar but not exactly the same things, and of course when you start looking at scalars and vectors, we'll examine the difference between speed and velocity in a little bit more detail, right? So what we've covered is we looked at derived quantities. We said that basically derived quantities often have a definition, a worded statement, and they also can be expressed in terms of a defining equation, which will basically allow you to calculate the, say, the value of a particular physical quantity. So for instance, if you want to find the density of a particular substance, and we have the mass of substance present, and we have the volume of the substance present, then we should be able to calculate the density of the substance. So now let's talk about the units of these, some of these derived quantities, and I'll leave these on the board. Now, as we mentioned before, the SI unit of fundamental or base quantities are called fundamental or base units. The SI unit of derived quantities are called derived units. So their units are called derived units, right? And how do we obtain the units of such physical quantities, right? Now, this is basically where the defining equations become very important, right? What exactly does that mean? If we know that in order to calculate density, we must divide the mass of a substance by its volume. Then in order to obtain the SI unit of density, we must basically do the same thing with the units of these quantities. Now let's talk about volume. What is the definition of volume? Volume is defined as the amount of space an object takes up, or the amount of space occupied by an object, right? That is the definition of volume. Now, what is the formula for calculating volume? The formula for calculating volume may vary, of course, depending on the shape of the particular object. So, for instance, if we're talking about something which is like a cuboid, of length L with W and height H, then the volume V is equal to the length times the width times the height. If we're talking about something in the shape of, say, a cylinder, however, that formula doesn't necessarily apply, right? So if we talk about a cylinder of height H and cross-sectional area A, then the volume is equal to the cross-sectional area times the height, right? And this goes back to my earlier statement where I said that if you're asked to define a particular quantity, then what is expected is that you state you make a worded statement and not write down an equation. Because, for instance, in the case of, say, volume, if you were asked to define volume and you wrote down V equals L by W by H, whereas that formula applies to the volume of a particular shape, it only applies to that particular shape. And therefore, it doesn't apply to other shapes, right? So again, the defining equation and the definition are not the same things, and the defining equation should not be used as a replacement or as a substitute for the definition, right? So, what we're basically saying is that in order, for instance, to calculate volume, say, of a rectangular shaped object or a cuboid, we multiply its length by its width by its height. Now, length, width, and height, of course, are all dimensions of length. And therefore, the unit, of course, or the SI unit rather, will be the meter. And so therefore, the SI unit of volume is obtained by multiplying the meter times the meter times the meter, which of course gives us the meter cube. So the SI unit of volume is the meter cube. And it doesn't matter whether the object is a cylinder or a cube or a sphere, the SI unit of its volume will be meter cube, right? Now let's go back to the density formula. So again, to calculate density, we divide mass by volume. And therefore, to calculate, or to determine rather, the units of density, the SI unit of density, then we must basically do the same thing with the units of mass and volume. So the SI unit of mass is the kilogram, and the SI unit of volume is the meter cubed, and therefore the SI unit of density is the kilogram per meter cube, which of course can be written in fractional form as that, or we can be written using index form. So this is kg m to the power of minus 3. So of course, whenever we're looking at units and we see a negative index, of course that implies that it was divided by. So this is kilogram per meter cube, which of course happens to be the SI unit of density, right? Let's talk about speed. So earlier we said that speed is defined as a rate of change of distance traveled with time, right? The defining equation for speed is equal to distance traveled over time taken, right? So in order to calculate speed, we divide the distance traveled by a body by the time taken. And in order to determine the SI unit of speed, we'll do the same thing with the respective SI units. So the SI unit of distance is the meter, symbol m. Again, at this level, we don't need to write out the word meter, right? And the SI unit of time, of course, is the second. And so we divide meter by second, we get meter per second in index form, written as m s to the minus 1. So that is the SI unit of speed and so on. What about force? The formula for calculating force is basically mass times acceleration. Acceleration. So the SI unit of force is obtained by multiplying the SI unit of mass by the SI unit of acceleration. Now the SI unit of mass is the kilogram, and the SI unit of acceleration, which of course is another derived quantity, is the meter per second squared. And so when you combine these two together, it basically gives us kilogram meter per second squared. So when you multiply the units, you simply put them together, right? Now, there are some derived quantities whose units are just combinations of the units of their respective base quantities. For instance, speed is a combination of the meter and the second, both of which are base units. And so the unit of speed, of course, is a meter per second, right? Earlier we looked at density or volume first. Volume is cubic meter, density, kilogram per meter cube. So those physical quantities, their units are just combinations of the respective base units, right? However, there are some physical quantities whose units are given special names. And these are usually names of people, one of which is force. The SI unit of force, of course, is equivalent to the kilogram meter per second squared. That is in terms of its base unit. But of course, we know that the SI unit of force is a Newton, and therefore the kilogram meter per second squared is equivalent to the Newton, right? Now, whenever we're writing these SI units, which are the names of famous people, if you're writing out the word, we generally write it with a lowercase letter. Unlike in English, we were taught that, proper nouns begin with a capital letter. In physics, if you have to write out the names of the units, we use a lowercase letter. But of course, if you're writing the symbol, we begin with an uppercase letter. So in this case, the SI unit of force is the Newton, symbol for which is an uppercase N, right? So later on, we will be able to, look at other derived units and express them in terms of their base unit equivalents. All right. Now, what are some other derived units, which are the names of special people? Some of these physical quantities whose units are the names of famous people, like energy, power, pressure. What is the SI unit of energy? The SI unit of energy is, of course, the joule, symbol J. The SI unit of power is the watt, symbol watt, W. And the SI unit of pressure is the Pascal, symbol PE. We can also add to this list. We can go a little bit further. We can talk about, for instance, like frequency. The symbol or the SI unit of which is the hertz. Again, the name of another famous person. Symbol is an HZ. So these are derived quantities, or a few of the derived quantities whose units aren't just combinations of the base units, but that combination of base units have been denoted by special names, which of course are the names of famous people who would have done a lot of work in these particular areas.